Hello, this is the fourth video of the series on single variable calculus, advanced calculus. And in this video, we're going to talk about some consequences of the completeness axiom. The first consequence of the completeness axiom that we're going to talk about is what we call the Archimedean property. And what the Archimedean property essentially tells us is that if you take the set of all positive integers, there is no upper bound for that set. In other words, if you take a real number c, then there is a positive integer n that is more than c. And if you take some positive number epsilon, there is some integer, positive integer m, that 1 over m is less than epsilon. The second part of this theorem easily follows from the first part. So we will go ahead and prove the second part, and then we'll talk about the first part, and then we'll talk about how the first part implies the second part. So the way we're going to prove this one is by contradiction. So we're going to assume that there is an upper bound for this set of integers, positive integers, and then we're going to get a contradiction. So let me talk about the proof on the side, and then we're going to write down the proof rigorously. So the idea of the proof is this. So let's assume this is not the case. So suppose, on the contrary, there is no positive integer n such that c is less than n. So that means if you basically write this down differently, you would get for every n in z plus, c is greater than or equal to n, which means z plus has an upper bound. So z plus is bounded above. Now, we know the sets that are bounded above have a supremum. So let's say the supremum is some value s. So, but the problem with having a supremum for natural numbers or positive integers is that if you take a positive integer very close to s, when you add 1, it goes beyond that. So n plus 1 goes above that. So here's now how we're going to articulate that. So by the completeness axiom, I'm going to call s as the supremum of z plus. This exists. So now, since s minus 1 is not an upper bound, s is the least upper bound, therefore s minus 1 is not an upper bound. Upper bound for z plus, there is some positive integer such that s minus 1 is less than n, because it's not an upper bound, therefore it is less than something in the set. And if we rewrite that, we get that s is less than n plus 1, and that means s is not an upper bound, because s is less than some positive integer. So this is the reason is n plus 1 is a positive integer. So this contradiction proves that there is a positive integer and that n is more than c. So that is the first part. The second part follows from the first part. It is just manipulating the inequality. If you manipulate the inequality, you get 1 over epsilon is less than m. So we're just gonna basically write that one. So by part A, there is some positive integer m such that 1 over epsilon is less than m. Then take the reciprocal of both sides. This would give you epsilon is more than 1 over m, which is exactly what we wanted to prove. So this is a very important property, the Archimedean property, and we're going to keep using that throughout this course. Now we're going to state some other theorems that are consequences of the Archimedean property, and I'm going to write down the sketch of the proofs for these next few theorems. We won't write down complete proofs for these, but we will write down the main ideas of the proof. Okay, so the next theorem is between every two consecutive integers, between n and n plus 1, there is no other integer. So first we're going to use proof by contradiction. So this would be proof by contradiction. So we're going to assume there is some m between n and n plus 1. This tells us 0 is less than m minus n less than 1. So this would be a contradiction. So how do we prove this one? Then prove that for every k in Z, if k is positive, then k must be at least 1. And this one can be done by induction on k. And if you take these two steps, then you would get the result. And it's really not difficult to show that if k is positive, it must be at least 1. It is true for 1, and if it is true for n, then it would be true for n plus 1 by induction. Okay, so the next theorem is dealing with the fact that if you have a set of integers, if it is bounded above, then it would have a maximum. And intuitively it makes sense. So because integers are discrete, they go up by 1. So if you have a supremum, if it doesn't go to infinity, then there would be one of these numbers that is the maximum in the set, meaning that it's the largest element of the set. So the sketch of proof is this. Since it is bounded above, apply the completeness axiom. And if you apply the completeness axiom, then you would get a supremum. So supremum of S would be some element S. Now, what we're going to do is we're going to have to show that this S is in fact in the set. Why is that in the set? Because if you take S, if you come one lower than that, so S minus 1, this is less than some M inside S. We know that. So this tells us S is less than M plus 1. But, so what I know is that M plus 1 is right here. And I know between M plus 1 and M, there is nothing in that range. So M is more than S minus 1 and M is in S. But M is less than or equal to S. We know that because S is the supremum. So that means M is somewhere around here. But there is no integer between M and M plus 1, which means there are no elements in the set that is in this range, which means S must be M. And that's exactly what we want. Because as long as the supremum is in the set, it would be the maximum element of the set. Okay, so the next theorem that we're going to discuss, and again this one would also be something that I won't write down a complete proof, is that if you take a real number C and add 1 to that, in this interval there would be one unique integer. So we have to show there is an integer, and then we have to show there aren't more than one integer. So first, the existence of an integer. So what we're going to do is we're going to take this set of all integers, such that integer n is less than C plus 1. Okay, so we are going to show that this set is bounded above and non-empty. So clearly it is bounded above because it's less than n is less than c plus 1. It is also non-empty. You can use the Archimedean property to show that. As soon as you show that, you know that there's a maximum. So let's say M is the maximum element of S, which means M is less than C plus 1, but M plus 1 is greater than or equal to C plus 1 because it's the maximum element. So that means M is greater than or equal to C. And that's exactly what we want. So M is inside C to C plus 1. So there is an element of the set S that is greater than or equal to C less than C plus 1, which means there's an integer in this interval C to C plus 1. So that is the existence of that integer. Uniqueness, to show uniqueness, as we have discussed before, we assume there are two, and then we're going to show that these two must be the same. So let's say, so this would be the uniqueness, the idea for the uniqueness. So let's say C is less than or equal to M, and it's also less than or equal to some other integer, and this is less than or equal to less than C plus 1. But what we know is that between M and M plus 1 there is no other integer, which means if M were to be less than K, then M would be less than M plus 1 would be less than or equal to K. But if that were to be the case, that would mean C plus 1, which is less than or equal to M plus 1, would be less than or equal to K. And that would mean C plus 1 is less than or equal to K, which is a contradiction. So this is exactly what we wanted to prove. We wanted to prove that there aren't two integers in that interval. There's just one integer inside that interval. And the reason is kind of clear because the length is 1. So the distance between these two must be at less than 1. And if the distance is less than 1, then they have to be the same. Because if you take two integers, they cannot have a distance of less than 1 unless they are exactly the same thing. Okay, so we're going to move on to the last thing we're going to talk about today, which is on sets being dense. So we will talk about what it means for a subset of R to be dense, and then we are going to talk about two examples of sets that are dense inside R. A subset S of R is said to be dense in R if for every two real numbers a less than b, there is an S in S for which S is in the interval a to b. So if you take the interval from a to b, there is something in S that is between a and b. In every interval, there is an element of the set. In that case, we say the set is dense. Similarly, if S is a subset of T, we say S is in T if for every two real numbers in T, there's an element in S that is between those two real numbers. So, the first example of a dense set inside R, the first, I guess, interesting example, is the set of all rationals. So what does that mean? It means if you take two real numbers a and b, we would like to find a rational in between them. So how do we do that? We are going to first clear the denominator. Let's just say n is positive so I can freely multiply by n. Now I have this interval. So since I have this interval and I want to show there is an integer inside that interval, all I need to do is to make sure that the length of the interval is more than 1. If the length of an interval is more than 1, based on what we have shown here in theorem 1.5, you would have some integer in there. And that would basically complete the proof. And this can follow from the Archimedean property. So now we are going to write down the proof, but we're going to have to start from the bottom. So let a less than b be two real numbers. So we're going to start from two real numbers. Now, by the Archimedean property, there is an integer n such that n is more than 1 over b minus a. So now, since b minus a is positive, we obtain n times b minus a is more than 1, because we can multiply by b minus a, which means nb is more than na plus 1. Now, by theorem, I believe 1.4, if we go back, or 1.5, there is an integer such that m is inside na plus 1, nb minus 1 to nb. So I guess we're going to make this one a little bit different. We're going to rewrite this a bit differently. nb minus 1 is greater than na. And this means na is less than nb, greater than or equal to nb minus 1. But nb minus 1 is more than na. So this means this is more than, this is m. na is less than m, less than nb, which means m over n is between a and b. And this is exactly what we wanted to show. We wanted to show between every two real numbers there is a rational, and that's exactly what we did. Okay, so finally we can do one more example on dense subsets of R. And this example deals with the set of irrationals being dense. So all we need to do is to take rationals and translate them by some irrational. In order to get an irrational number, you could just take some rational number, let's say 7/8, and then add root 2 to that. You get another irrational number. And this is something you must have seen in an introduction to proof course. So the sketch of proof would be this. We take some a and some b, and we are going to make sure that some rational plus root 2 is in between them. We can do that because of the fact that set of rationals now are dense. So because set of rationals are dense, we can choose some rationals between a minus root 2 and b minus root 2. So here's now how we're going to write down the solution. So let a less than b be two real numbers. Since a minus root 2 is less than b minus root 2, by the previous theorem, theorem 1.6, there is a rational number r such that r is between a minus root 2 and b minus root 2, which means a is less than r plus root 2, and that's less than b. Since r is rational and root 2 is irrational, r plus root 2 is irrational. So we found an irrational between a and b. Therefore, Q complement is dense in R. And that's exactly what we wanted to prove. So this brings me to the end of this video. If you would like to continue with this class, feel free to subscribe